Lecture 5, Application of a Continuous Time Markov Chain in Simple Markovian Queuing Models. The first lecture we have discussed the definition of a stochastic process, in particular continuous time Markov chain. Then we have considered the Kolmogorov differential equation, Chapman-Kolmogorov equations, the transient solutions for the CTMC. The second lecture we have discussed the special case of continuous time Markov chain, that is a birth-death process. We have discussed in lecture 2. Lecture 3, the special case of birth-death process, which is a very important stochastic process, that is Poisson process, is discussed in the lecture 3. The lecture 4, we have discussed the MM1 queuing model, that is a very special and important queuing model, and the underlying stochastic process for the MM1 queuing model, that is a birth-death process with the birth rates are lambda and death rates are mu. In the fourth lecture we have discussed only the MM1 queuing model. In this lecture we are going to consider the other simple Markovian queuing models as an application of a continuous time Markov chain. So, in this lecture I am planning to discuss, other than MM1 queuing model, I am going to discuss a simple Markovian queuing models, starting with the MMC infinity queuing model, then the finite capacity model Markovian setup, MM1N queuing model. Then I am going to discuss the multi-server finite capacity model, that is MMCK queuing model. After that I am going to discuss the loss system, that is MMCC model. For an infinite server model, that is MM infinity, also I am going to discuss. At the end I am going to discuss the finite source Markovian queuing model also, whereas the other 5 models the population is infinite source. So, the last one is a finite source Markovian queuing model, also I am going to discuss as the application of continuous time Markov chain. The first model is a multi-server infinite capacity Markovian queuing model. The letter M denotes the inter-arrival time is exponentially distributed with parameter lambda. The service time by the each server, that is exponentially distributed with the parameter mu, and all we have more than one servers. Suppose you consider as a C, where C is a positive integer, and all the servers are identical, and each server is doing the service which is exponentially distributed with the parameter mu, which is independent of the all other servers, and the service time is independent with the inter-arrival time also. With these assumptions, if you make a random variable x of t is the number of customers in the system at any time t, that is a stochastic process. Since the possible values of number of customers in the system at any time t, that is going to be 0, 1, 2 and so on, therefore it is a discrete state, and you are observing the queuing system at any time t, therefore it is a continuous time. So, discrete state continuous time stochastic process, and if you observe, the system is keep moving into the different states because of either arrival or the service completion from the any one of the C servers. So, suppose there are no customer in the system moves from the state 0 to 1 by one arrival. So, the inter-arrival time is exponentially distributed, therefore, the rate in which the system is moving from the state 0 to 1 is lambda. Like that you can visualize the rates for system moving from 1 to 2 2 to 3 and so on. Whereas whenever the system size is 1, 2 and so on till C, since we have a C number of servers in the system, whoever is entering into the system, they will start getting the service immediately. Suppose the system goes from state 1 to 0, that means the customer enter into the system and he get the service immediately, and the service time is exponentially distributed with the parameter mu. Therefore, whenever the service is completed, the system goes from the state 1 to 0, therefore the rate is mu. Whereas from 2 to 1, there are two customers in the system and both are under service. At any time, if any one of the servers complete his service, then the system moves from 2 to 1. So, the service completion will be minimum of the service time of both the servers. Since each server is doing the service exponentially distributed with the parameter mu, therefore, the minimum of 2 exponential and both are independent also. Therefore, that is also going to be exponentially distributed with the sum of parameters. So, it is going to be parameter will be mu plus mu, that is 2 mu. So, the system moves from the state 2 to 1 will be the rate will be 2 mu. Like that it will be keep going till the state from C to C minus 1. That means we have C servers. Therefore, whenever the system size is also less than or equal to C, that means all the customers are under service. Now, we will discuss the rate in which the system is moving from the state C plus 1 to C. The system state is a C plus 1, that means the number of customers in the system, that is C plus 1. We have C servers, therefore, one customer will be waiting for the service, waiting in the queue. Therefore, the system is moving from C plus 1 to C, that is nothing but one of the server completed the service out of C servers. Therefore, the rate will be, the service time, completion service time will be exponential distribution with the parameter C mu, not C plus 1 mu. It is we have only C servers. Therefore, the minimum of exponentially distributed with the parameters mu and so on with the C exponentially distributed random variables. Therefore, that is going to be exponential distribution with the parameter mu plus, there are C mu's, therefore, it is going to be C mu. Like that, the rate will be, the death rate will be C mu after C plus 1 onwards. Whereas from 0 to C, it will be mu, 2 mu, 3 mu and so on till C mu. After that, it will be a C mu from the state from C plus 1 to C plus 2 to C plus 1 and so on. And if you see the state transition diagram, you can observe that this is a birth-death process. So, before that let me explain what is a MMC infinity means. Whenever C customers or C servers or any one of the C servers are available, then the customers will get the service immediately. If all the C servers are busy, then the customer has to wait till any one of the C servers are going to be completing their service. So, that is the way the system works. Therefore, you will have the system size, the underlying stochastic process is going to be a birth-death process. It is a special case of a continuous time Markov chain, because the transitions are only the neighbors transition with the forward rates, that is lambda, and the backward rates or the death rates are going to be mu, 2 mu and so on. Therefore, this is a special case of a continuous time Markov chain, the underlying stochastic process for the MMC infinity model, that is a birth-death process. The birth rates are lambda, whereas the death rates depends on the n. the mu n is a function of n, therefore it is called a state dependent death rates. It need not be the function n times mu, it can be a function of n, then we can use the word state dependent. So here it is a linear function. So state dependent death rates, and the death rates are n times mu whenever n is lies between 1 to c. And the mu n is going to be c times mu for n is greater than or equal to c. That you can observe it from the state transition diagram also. The death rates are going to be c mu, here also c mu, and so on. Therefore, this is a birth death process with the state dependent death rates. Now our interest is to find out the steady state or equilibrium solution. Since it is an infinite capacity model, if you observe the birth death process with the infinite state space, then you need a condition so that the steady state probabilities exist. So whenever lambda by c mu is less than 1, whenever lambda by c mu is less than 1, you can find out the limiting probabilities. So sometimes I use the letter p n, sometimes I use the word pi n, both are one and the same. So you find out the steady state probability by solving a pi q is equal to p q is equal to 0 and the summation of a pi is equal to 1. And if you recall the birth death process steady state probabilities, the pi naught has the 1 divided by the series. Whenever the denominator series converges, then you will get the pns. So either I use a pns or pi n's, both are one and the same. So here summation of a pi is equal to 1 and the p, if you make a vector p times a q is equal to 0, if you solve that equation, and the denominator of a p naught, that expression, that is going to be converges only if lambda divided by c mu is less than 1. So therefore, whenever this condition is there, the queuing system is stable also. If you put c is equal to 1, you will get the MM1Q. So using the normalizing condition, you are getting the P naught, and the P naught is 1 divided by this. So this is a series. So this series is going to be converges only if this condition is satisfied. So by solving that equations, you are getting Pn's in terms of P naught, and using normalizing constant, you are getting a P naught. Therefore, this is a steady state, also known as the equilibrium solution for the MMC infinity model. So here we are using the birth death process with the birth rates are lambda and the death rates are given in this form, and use the same logic of the stationary distribution for the birth death process. Using that, we are getting the steady state or equilibrium solution for the MMC model. Other than the steady state probability, we can get some more measures. The first one is the probability that the arriving customer has to wait an arrival. What is the probability that the arriving customer has to wait on arrival? So that means the number of customers in the system is greater or equal to C. Then only the customer has to wait. So the probability, you add the probability of Pn, here is a mistake, P suffix n, where n is running from C to infinity. If you add all those probabilities, that is going to be Pc divided by 1 minus rho. And this probability is known as a Erlang C formula for a multi-server infinite capacity model. That I am denoting with the letter C of C comma lambda by mu, because you need a number of servers in the system and you need a lambda as well as mu. If I know this quantity, I can find out what is a Erlang C formula. This is very important formula. Using that, you can find out what is the optimal C, such a way that the probability has to be minimum. You can find out what is optimal number of servers is needed to have some upper bound probability of arriving customer has to wait. Therefore, this Erlang C formula is very useful in performance analysis of any system. The next quantity is NQ, denotes the number of customers in the queue. So, either I use the letter N suffix Q, earlier I used the letter Q itself. So, for that I am finding the joint distribution of what is the probability that the number of customers in the queue is J and the waiting time is going to be greater than 0. W is used for the waiting time. So, the waiting time is going to be greater than 0. That is same as the number of customers in the system, that is C plus J. What is the probability that J customers in the queue as well as the waiting time is greater than 0? That is same as what is the probability that C plus J customers in the system. Do the little simplification. So, you will get this joint probability in terms of Erlang C formula. So, using that I am finding the conditional probability. What is the conditional probability that J customers in the queue given that the waiting time is greater than 0. If I do little simplification, I will get 1 minus rho times rho power j, where rho is lambda divided by C mu. This is nothing but the probability mass function of a geometric distribution. This is the probability mass function of a geometric distribution. Therefore, this conditional probability is geometrically distributed with the parameter rho. From this you can find out the expected number of the next measure is the expected number of busy servers. What is the average number of busy servers? That is nothing but the summation of n equal to 0 to c minus 1 n times Pn. That means whenever the system size is less than c, only those many servers are busy and with the probability. Whenever n customer or more than n customers in the system, all the C servers are going to be busy. Therefore, C times Pn. If you simplify, you will get a C times rho. So, that is the expected number of busy servers. Once I know the expected number of busy servers, I can find out what is the expected number of idle servers also. It is a negation. That is the expected number of ideal server is nothing but expectation of it is a random variable. So, ideal number is nothing but there are totally C servers in the system. Therefore, C minus BC servers are capital B. Therefore, C minus B is same as I. So, the expectation satisfies the linear property. Therefore, expectation of I is same as expectation of C minus B. C is a constant and B is a random variable. Therefore, it is a C minus expectation of a B. Expectation of B, just now we got C times rho. Therefore, the expected number of ideal server is C times 1 minus rho. So, other than stationary distribution, for the MMC model, we are getting what is the probability that arriving customer has to wait, and we are getting the conditional probability of j customers in the queue given that waiting time is greater than 0, as well as these expected quantities we are getting. Also, we can find out what is the expected number of customers in the system. That is nothing but expected number is nothing but expected of the busy servers plus expected number in the queue. Earlier I used the notation n suffix q and q are both one and the same. So, I can compute what is the expectation of q, do the little simplification, then I can substitute expectation of q here. Therefore, I will get expected number of customers in the system. That involves the Erlang C formula. So, this Erlang C formula is used to get the expected number of customers in the system, and then later we can do some optimization over the probability expected number with the specified C and lambda by mu. So, using Little's formula, I can find out the expected time spent in the system. because I know what is arrival rate, and from the stationary distribution I got expected number in the system in a steady state. Therefore, since I know lambda and expectation of n, I can get expectation of r, where r is the response time or sojourn time or total time spent in the system. So, that expectation is going to be expectation of n divided by lambda. Do little simplification, you will get expectation of r. You can apply the Little's formula in the Q level also. So, this is a system level and you can apply the Q level also. So, lambda times expectation of waiting time is same as expectation of a number of customers in the queue. So, expectation of a waiting time or average waiting time is same as expectation of a queue divided by lambda. So, using since the MMC infinity Q, the underlying stochastic process is a birth-death process. Therefore, we are getting all the measures using the birth-death logic. Next, I am going for the finite capacity. So, the n is the capacity of the system. That means whenever the customers arrives and find the queue full, that customer will be rejected. Therefore, at any time the number of customers in the system, if you make it as a random variable, and that random variable takes the possible values from 0 to capital N. Therefore, the state space is finite. The number of customers in the system any time t, that is a random variable, and you will have a stochastic process. And since the inter-arrival time is exponentially distributed, service is exponentially distributed, only one server, finite capacity. Therefore, the underlying stochastic process is a birth-death process with the birth rates lambda, the death rates mu. If you see the Q matrix for this one, infinitesimal generator matrix, that is a diagonal matrix with the all the off diagonals or lambdas as well as mu, and the diagonals are minus lambda plus mu except the first term and the last term, except the first row and the last row. Our interest is to get the stationary distribution. Later I am going to explain the time dependent solution also. So, to get the stationary distribution, either you write the pi q is equal to 0 and the summation of pi a is equal to 1 and solve that, or you write the balance equation. The pi q is equal to 0, that will land up a balance equation. So, some books writes this as a balance equation. What is the inflow rate and what is the outflow rate? Both are going to be same whenever the system reaches the equilibrium solution, equilibrium state. Therefore, the outflow is a lambda times this, the inflow is mu times lambda 1. Like that you can go for understanding the balance equation for this state and second and so on. And this also satisfies the time, this is also called satisfying the time reversible equation. Therefore, one can use the time reversible property of a birth-death process. So, you can find out the pi a is easily using the time reversible equation itself. You do not want to use a pi q is equal to 0, instead of that you can write the time reversible equation since it is satisfied by all the states. Now, you can use the summation of pi a is equal to 1, I starting from 0 to n. Therefore, you will get a pi naught, and here the birth-death process with the finite state space. Therefore, the pi naught will be 1 divided by the denominator series, that is a finite series, finite terms in it. Therefore, it is always converges immaterial of the value of lambda and mu. Therefore, you will get a pi naught without any restriction over lambda and mu. So, once you get the pi naught, you can get pi a is in terms of pi naught. Therefore, that is a 1 minus rho divided by 1 minus rho power n plus 1 times rho power I, where rho is lambda by mu. So, this is the the underlying stochastic process is a birth-death process with the birth rates lambda and death rates mu. So, you can use all the concepts of the birth-death process and you can analyze the system in a easy way. So, this is a steady state probability. Once you know the steady state probability, you can get the other measures also. Here, the other important thing is called the effective arrival rate. That means the system, the queuing system is a finite capacity. So, maximum n customers can wait in the system and the service rate is mu, the arrival rate is lambda from the infinite population. So, whenever the system size is full, the customer is rejected. Therefore, there is a rejection. After the service is completed, the system leaves the system. So, the effective arrival rate nothing but what is the rate in which the system is the customers are entering into the system. So, there is a partition here. So, the effective arrival rate is lambda f. That rate will be what is the probability that the system is not full multiplied by the arrival rate lambda, that is going to be the lambda effective. Whenever the system is not full, that proportion of the time or the probability is 1 minus pi n, where pi n is the steady state probability. Just now we got it. From here you can get a pi suffix n, that is the probability that the system is full, and 1 minus pi n is the probability that the system is not full, and multiplied by the arrival rate, that is going to be the lambda effective. And you can also find out the throughput. Throughput is nothing but what is the rate in which the customers are served per unit of time. The service rate is mu, and this is the probability that the system is not empty, 1 minus pi naught. Therefore, 1 minus pi naught times mu, that is the rate in which the customers are served in the MM1 n system. Whenever the system is not full, whenever the system is not empty, multiplied by that probability multiplied by mu, that is going to be the throughput. By using the time reversible equation, the mu times 1 minus pi naught you can get in terms of lambdas equivalent also, but the throughput is the service rate multiplied by what is the probability that the system is not empty. Since it is a finite capacity system, one can find out the blocking probability also. Blocking probability is nothing but the probability that the customers are blocked. The customers are blocked whenever the system is full. Therefore, the blocking probability is same as the probability that the system is full, that is pi a. Once we know the steady state probabilities, you can find out the average number of customers in the system, and using the Little's formula you can get expected time spent in the system by any customer divided by not lambda, it is lambda effective, because the effective arrival rate is used in the Little's formula, not the arrival rate. For a MM1 infinity system, the effective arrival rate and the arrival rate are one and the same, because there is no blocking. Therefore, the probability of 1 minus pi n, that is equal to 1 only. Therefore, the effective arrival rate and the arrival rate are same for a infinite capacity system, because there is no blocking. For a finite capacity system, the effective arrival rate has to be computed. Similarly, we have to go for finding the lambda effective for the MMCK model also. So, other than stationary distribution or equilibrium probabilities, we are getting the other performance measures using the birth-death process concepts. Now, I am moving into MMCK model, queuing model. So, here the change is instead of one server in the MM1 model, you have more than one servers C, and you have a finite capacity, that is capital K, capacity of the system. So, the arrival follows the Poisson process, service is exponential, we have C identical servers, the capacity is capital K, and this is a scenario in which whenever the system size is less than C, it will be routed into the ideal server. If it is greater or equal to C, that means all the servers are busy, that means the customer has to wait. But if the system size is full, that means C customers are under service and K minus C customers are waiting in the queue for the service, then whoever comes, it will be rejected, forced to leave the system. Therefore, you have a waiting as well as a blocking. Because it is a finite capacity, there is a blocking, and since you have always we choose K such that it is K is always greater or equal to C. If K is equal to C, then it is a lost system. If K is greater than C, then K minus C customers maximum can wait in the system, in the queue. Therefore, the underlying stochastic process, here the stochastic process is again number of customers in the system at any time t. Therefore, this stochastic process is also going to be a continuous time Markov chain. Because of these assumptions, inter-arrivals or exponential distribution service, each service by each server is exponentially distributed and all are independent and so on. So, with these assumptions, this stochastic process is a continuous time Markov chain, and at any time only one forward or only one backward the system can move. Therefore, it is going to be a birth-death process also, and the birth rates are lambda because it is an infinite source population. So, all the lambda n's are going to be lambda, whereas the death rates are state dependent, that is going to be n times mu, lies between 1 to C. From C to K onwards, it is going to be C mu. So, I have not drawn the state transition diagram for MMCK, but you can visualize the way we have a MM1 N and a MMC model. So, the combination of that is going to be the state transition diagram. Since it is a finite capacity model, it is easy to get the steady state and the equilibrium solution. So, first you solve pi q is equal to 0, that means you write pi n's in terms of pi naught and use a normalizing constant, summation of pi a is equal to 1, using that you will get pi naught. So, I have not written here. So, use the normalizing constant, the summation of pi a is equal to 1, get the pi naught, then substitute pi naught here, therefore, you will get pi n in terms of pi n completely. After that, you can get the all other average measures the way I have explained the MM1n and the MMC infinity, the combination of that. You can get the average number of customers in the system, average number of customers in the queue, that is n minus C times pi n. The combination, the summation goes from C to K, and the average time spent in the system. Since it is a finite capacity, you have to find out the lambda effective arrival rate, that is 1 minus, its a capacity is capital K, therefore 1 minus pi k, that is the probability that the system is not full. So, the effective arrival rate is lambda times 1 minus pi k. Substitute here and get the average time spent in the system. And similarly, you can find out the average time spent in the queue also using the Little's formula. Now, I am moving into the fourth simple Markovian queuing model. First, I started with the MMC infinity, MM1n, then I did MMCK, and now I am going for capital K is equal to C, that is loss system. It is not a queuing system because we have a C servers and the capacity of the system is also C. Example is, you can think of a parking lot which has some C parking lots and the cars coming into the system, that is if you make the assumption is the inter-arrival time is exponentially distributed and the car spending time in each parking lot that is exponentially distributed, then the parking lot problem can be visualized as the MMC loss system. So, here we have a C identical servers, no waiting room. So, since it is a C capacity and a C waiting room, you can think of a self-service with the capacity C, that also you can visualize. So, here the inter-arrival times are exponentially distributed and the service by each server that is exponentially distributed with the parameter mu. Therefore, the system goes from 2 to 1, 1 to 0, so on. It is going to be how many customers in the system and completing their service. Therefore, the time is exponentially distributed with the sum of those parameters accordingly. Therefore, it is going to be 1 mu, 2 mu till C mu. Since it is a finite capacity and so on, it is a irreducible model, positive recurrent. Therefore, the steady state probability exists, limiting probabilities also exist, and that is same as the equilibrium probabilities also. Therefore, by using a PQ is equal to 0 and a summation of PA is equal to 1, you can get the steady state or equilibrium probabilities, that is PNs. The P suffix C, that is nothing but the probability that the system is full, and that is same known as the Erlang B formula. So, this is also useful to design the system for a given or what is the optimal C, such a way that you can minimize the probability that the system is full. For that you need this formula, therefore, to do the optimization problem over the C. And here we denote a P suffix C, that is a Erlang B formula. Whereas Erlang C formula comes from the MMCK model. For the loss system, we will get the Erlang B formula. The fifth model, that is MM infinity. It is not a queuing model because the servers are infinite, unlimited servers in the system. Therefore, the customer whoever enter, he will get the immediately service. The service will be started immediately. Whereas the service time is exponentially distributed with the parameter mu by the each server. All the servers are identical. The number of servers are infinite here. Therefore, you will have the underlying stochastic process for the system size, that is a birth-death process with the birth rates are lambda, because the population is from the infinite source. The death rates are 1 mu, 2 mu and so on, because the number of servers are infinite. So, the model which I have discussed in today's lecture, all the 5 models are the underlying stochastic process is a birth-death process. This is the simplest Markovian queuing models. We can get the steady state distribution, use the same theory of birth-death process. And if you observe this steady state probabilities is of the same Poisson, this of the form, that is a probability mass function of a Poisson distribution. Therefore, you can conclude in a steady state a number of customers in the system, that is Poisson distributed with the parameter lambda by mu, because the probability mass function for the pi n is the same as the probability mass function of exponentially distributed random variable with the parameter lambda by mu. Now, I am explaining the transient solution of a finite birth-death process. So, using this, one can find out the transient solution of the birth-death process, which I have discussed today's class, MM1N, MMCK and MMCC also. So, the logic is same. That means you have a birth-death process with the finite state space. Therefore, the Q matrix is going to be a degree, whatever be the number of states in the state space, and it is going to be a tridiagonal matrix, and you know the lambda n's and mu n's, birth rates as well as the death rates. And the birth rates and the death rates are going to be different for these three models. There are many literature over the transient solution of a finite birth death process, started with Murphy and O'Donoghue. He uses the polynomial method, and in 1978 Rosenlund also found the transient solution for the finite BDP using again the different polynomial methods. And Chiang in 1980 he made a matrix method to get this transient solution. Then later Van Doon gave the solution using a spectral representation method, and Nikiforov et al. 1991 he also gave the transient solution using orthogonal polynomial. And later Kijima also gave the solution using eigenvalue methods. So these are all the literatures for getting the transient solution of a finite birth death process, and here I am going to explain how to get the transient behavior of a MM on NQ in a very simplest form, even though there are this many literature and many more literatures for the finite birth death process, but here I am explaining the overview of how to get the transient behavior of MM on NQ. And this is by O.P. Sharma and U.C. Gupta. It appears in Stochastic Processes and Their Applications, volume 13, 1982. So what this method work, you start with the forward Kolmogorov equation, that is pi t, pi dash t, that is started with pi dash of t, that is equal to pi of t into Q matrix, where pi is the matrix and pi dash is the with the derivatives and the Q is the infinitesimal matrix. Take a forward Kolmogorov equation, then use the Laplace transform for each pi n of t. You take the here the pi dash of t is the vector, it is a distribution of a x of t, therefore this is a vector and this is a vector, and the Q is the matrix, not the matrix which I said wrongly. So this is a vector and this is a vector and the Q is the matrix. So take a Laplace transform for each probability, where the pi n of t, that is nothing but so the pi of t is a vector that started with pi naught of 0 t, pi 1 of t, and so on, pi n of t, where pi n of t is nothing but what is the probability that, the same notation I started when I discussed the birth death continuous time Markov chain, what is the probability that n customers in the system at time t. It is an unconditional probability distribution. So pi n of t is the probability that n customers in the system at time t, and using pi n of t you get the vector and you make a forward Kolmogorov equation, pi dash of t is equal to pi of t times q, and take a Laplace transform for each pi n of t that exists, because this is a probability and the conditions for the Laplace transform of this function satisfies. You can cross check, therefore you are taking a Laplace transform, this is going to be a function of theta. Before taking a Laplace transform you need a initial condition also. So at time 0 you assume that no customer in the system. At time 0 no customer in the system, that means x of 0 is equal to 0. Therefore that probability is going to be 1 and all other probabilities are going to be 0. That is the initial probability vector. So use this initial probability vector and apply it over the forward Kolmogorov equation, taking a Laplace transform you will get the system of algebraic equation. Since we are using the pi naught of 0 is equal to 1, you will get the first equation with the term 1 and all other terms are going to be 0. And you know the Laplace transform of the derivative of the function. So you substitute you take a Laplace transform over the forward Kolmogorov equation with this initial condition as well as pi n's of 0 is equal to 0 for n not equal to 0. So, you will have a algebraic equation, that is a n plus 1 algebraic equations as a function of theta. You have to solve this algebraic equation, system of algebraic equation in terms of theta. Once you are able to solve this and take an inverse Laplace transform, and that is going to be the system size at any time t. You can start saying that this is going to be of the solution A times alpha n and B times beta power n, where alpha and beta are given in this form, where alpha is equal to this plus something and the beta is equal to minus something, minus square root of this expression. So, you have a alpha as well as beta. Now, what do you want to find out? If you find out the constant A and B, you can get the Laplace transform of pi n of t. Then you take a inverse Laplace transform and you get the pi n of t. So, for that you need the determinant of a matrix of this form, and here this is nothing but all these values are death rates and these are all the birth rates, and this is corresponding to the MM1N model, and the same logic goes for the transient solution of a MMCK as well as a MMCC. So, instead of these lambdas and mu's, you will have a corresponding birth rates and the death rates, but ultimately you will have a n plus 1 matrix determinant as a function of theta. And since these three models are going to be irreducible, positive recurrent, the stationary probability and limiting probabilities exist. Therefore, this determinant is going to be always of the form theta times some other function as a degree, as a polynomial of degree n in a function of theta. So, this theta is corresponding to the stationary probabilities or the limiting probabilities. Therefore, always you can get the n plus 1th degree matrix, 1th order matrix determinant, that is theta times the polynomial of degree n as a function of theta. For the MM1N model, the birth rates are lambda and the death rates are mu, and you can get this polynomial also in the form of product. The product of theta plus lambda plus mu times alpha of n comma k square root of lambda mu, where alpha of n comma k is nothing but the k roots of nth degree Chebyshev polynomial of second kind. There is a relation between the birth death process with the orthogonal polynomial. For instance, the MM1N model, the finite capacity MM1N model, the corresponding orthogonal polynomial for this birth death process is the Chebyshev polynomial of the second kind. Similarly, you can say the orthogonal polynomial corresponding to the MMCC model, that is a Charlier polynomial. Like that we can discuss the orthogonal corresponding orthogonal polynomial for the finite capacity birth death processes. So, here for the MM1N model, this is related to the Chebyshev polynomial of second kind, that is UN of x. So, once you are able to get the Chebyshev polynomial roots, and that roots is going to play a role in the product form, and that is going to be the polynomial. Note that this polynomial has a distinct real factors. Therefore, you can use the partial fraction, then you take a inverse Laplace transform, finally you can get the pi n of t. I am skipping all the simplification part, and the main logic is this n plus 1th order matrix determinant, and that determinant has the factors, and those factors are related to the Chebyshev polynomial roots. So, once you use all those logics and use the partial fraction, then finally you take a inverse Laplace transform. For lambda is not equal to mu, you will get a steady state or stationary probabilities plus this expression, and this is a function of t, e power minus lambda plus mu times t plus 2 times square root of lambda mu times t cos of r by n plus 1, and denominator this expression multiplied by this, and here this result is related to the initial condition 0. That means at time 0 the system is empty. If the system is not empty, then you will have one more expression here, sine of this minus another term. So, that is you will have a little bigger expression for system size is not empty, and this theta times this, that will give the corresponding partial fraction and so on, inverse Laplace. It will give the terms which is independent of t, and that is related to the steady state probabilities, because if you put t tends to infinity, these quantities are greater than 0. So, as a t tends to infinity, the whole terms will tends to 0. Therefore, as a t tends to infinity, you will have a pi n of t is equal to this expression, and this is valid for rho is less than 1. With that condition rho is less than 1, with the condition rho is less than 1, those terms will tends to 0, and you will have only this term, and that is going to be the steady state or limiting probabilities for MM1n model. If you make also n tends to infinity along with the t tends to infinity, you will have pi n's, that is the steady state probability for the MM1 infinity model. So, even though I have explained MM1n transient solution in a brief way, but the same logic goes for the MMCK model also. The only difference is this determinant has the lambdas, and instead of mu's you will have mu, 2 mu, 3 mu and so on, and instead of the Chebyshev polynomial you will end up with the Charlier polynomial. But there is a difference between this MM1n model and the MMCK model transient solution. Since the Chebyshev polynomial has a closed form roots, you can find out the factors. So, here these are all the factors, and you know the factors as well as you can get the closed form expression for the MM1n transient solution, whereas a Charlier polynomial does not have a closed form roots. Therefore, you will end up with the numerical result for the transient solution for MMCK model. Application of a continuous time Markov chain, that is a finite source Markovian queuing models. This model is also known as a machine repairman model, and you can think of these pieces are nothing but the machines, and this is nothing but the repairman. And here the scenario is we have k PCs, and each PC can give a print job, and the inter arrival of print jobs, that is exponentially distributed by the each PC. Therefore, the print jobs that is follow a arrival process, that is a Poisson process with the parameter lambda from each PC, and once the print jobs come into the printer, it will wait for the print, and the time taken for the each print, that is also exponentially distributed with the parameter mu. And here there is another assumption: before the first print is over by the same PC, it cannot give the another print command. Therefore, after the print is over by any one particular print job of any PC, then the things will go back to the same thing. Then with the inter arrival of print jobs generated, that is exponentially distributed, then the print job can come into the printer. So, with these assumptions, you can think of the stochastic process, that means a number of print jobs at any time t in the printer, that is going to form a stochastic process, and with the assumption of inter-arrival of print jobs, that is exponential, and actual printing job, that is exponentially distributed, and so on. Therefore, this is going to be a birth-death process with the birth rates are k times lambda and k minus 1 times lambda and so on, whereas the death rates, that is mu, because we have only one repair. So, this is nothing but a system size, number of jobs in the printer. So, therefore, that varies from 0 to capital K, because we are making the assumption more than one print job cannot be given by the same PC before the print is over. And from 0 to 1, the arrival rate will be any one of the k PCs, therefore, the arrival rate is k times lambda, and already one print job is there in the system printer, therefore, out of k minus 1 PCs, one print job can come, therefore, the inter-arrival time, that is exponentially distributed with the parameter k minus 1 times and lambda and so on. So, this is the way you can visualize the birth rates, whereas the death rates are mu. Once you know the birth rates and the death rates, you can apply the birth-death process concept to get the steady state probabilities. So, here we are getting the pi a is in terms of pi naught, and using summation of pi a is equal to 1, you are getting the pi naught also. And once you know the steady state probability, you can get the all other measures. So, the difference is in this model it is a finite source, therefore, the birth rates are the function of, it is a state dependent birth rates, whereas the death rates are mu's only. Simulation of a queuing model, I will do it in the next lecture. The summary of today's lecture, I have discussed the simple Markovian queuing models other than MM1 infinity that I have discussed in the lecture, previous lecture, and the stationary distribution and all other performance measures using the birth-death process we have discussed for these queuing models. And finally, I discussed the finite source Markovian queuing model also. These are all the reference books. Thanks.